Welcome to Lecture 9. This week we're going to start talking about an important idea called Eigenvalues and Eigenvectors. And then using those, we'll do our first type of factorization of a matrix when we talk about the diagonalization of a matrix. And then in the third topic of today's lesson, we'll use the ideas from the last lesson about complex numbers and extend that to complex vector spaces. First, let's talk about eigenvalues and eigenvectors. And I start with the statement that matrices do things to vectors. By this I mean, if we take a vector and we multiply on the left by a matrix, then we're going to get a new vector. For example, if we start with the vector 1, 1, and we multiply it on the left by the matrix 3, minus 2, minus 1, 4, then we're going to get the new vector 1, 3. So it looks like we're taking the green vector, we're stretching it, and we're rotating it anti-clockwise. Let's try another vector. Let's start with the vector 1, 0. Same matrix, it's always going to be the same matrix. If we multiply on the left by this matrix, what happens to the vector 1, 0? This time we get the vector 3 minus 1. So again, we're stretching it, but this time we're rotating clockwise. Let's try another vector. What about the vector 0, 1? Where does this go? If we do matrix multiplied by vector, we get minus 2, 4. Again, we're stretching it. This one is rotating anti-clockwise. So some of them are rotating anti-clockwise and some of them are rotating clockwise. There are some special vectors, for example, the vector 2, 1, when if we multiply on the left by the matrix, we don't rotate at all, we just do stretching. Our matrix 3 minus 2 minus 1, 4 multiplied by this special vector 2, 1 is equal to 4, 2. In other words, we just have a number multiplied by the vector that we started with. Vectors which have this special property that when we multiply them on the left by a matrix and they just give us a number multiplied by the vector we started with are called eigenvectors. Let's give the former definition. If A is an n by n matrix, so it has to be a square matrix, then a non-zero vector x is called an eigenvector of A if ax is a scalar multiple of x. In other words, if ax is equal to lambda x for some number or some scalar lambda. And let me just emphasize, we're only interested in non-zero vectors x. Every time we talk about an eigenvector, we can't take the zero vector, it has to be a non-zero vector. This number, this scalar lambda, is called an eigenvalue of the matrix A, and the vector x is said to be an eigenvector corresponding to lambda. Let me just repeat that. The zero vector cannot be an eigenvector. An eigenvector must be a non-zero vector. And let me just talk about the definition quickly. I've used the definition ax is equal to lambda x. Matrix multiplied by vector is just equal to number multiplied by this special vector, which is called an eigenvector. Some books use similar notation. Some books use lambda I minus a multiplied by x is the zero vector, and some use a minus lambda I multiplied by x is equal to the zero vector. And of course, all three of these are the same. We will use whichever formula makes sense to us in each particular instance. So, for example, let A be the matrix 1, 6, 5, 2. Let U be the vector 6 minus 5, and let V be the vector 3 minus 2. are U and V eigenvectors of A? To answer this question, we're going to calculate AU, and does this give us a number multiplied by U? And we're going to calculate AV. And again, we're going to ask, does this give us a number multiplied by V? So let's try it. A multiplied by U gives us minus 2420. I'll leave that for you to check. And that is minus 4 multiplied by U. So that tells us that U is an eigenvector of A corresponding to the eigenvalue lambda is equal to minus 4. And what about V? What do we get if we multiply A by V? We get minus 911. And that is not equal to a constant multiplied by 3 minus 2. So we can see from this that V is not an eigenvector of A because AV is not a multiple of V. Now, let me remind you that we've seen that if a determinant of a matrix B is not equal to 0, then that means B is invertible, and therefore the only solution to the homogeneous linear system Bx equal to 0 is the trivial solution. Why? Well, if B is invertible, we can just do B inverse on each side. We will get B inverse Bx is equal to B inverse 0. B and B inverse cancel. B inverse 0 is just a 0. So if B is invertible, if the determinant of B is not equal to 0, then the only solution to Bx equal to 0 is x equal to 0. Turn this around. That's logically the same as saying that if there exists a non-trivial solution to Bx equal to 0, then the determinant of B must be 0. Or for us, if there is a non-zero vector x, such that lambda I minus a x is equal to 0, if there exists a non-trivial solution, then the determinant of this matrix must be equal to 0. Let's write that as a theorem. If A is a square n by n matrix, then lambda is an eigenvalue of A if and only if it satisfies the equation the determinant of lambda I minus A is equal to 0. This equation is called the characteristic equation of the matrix A. This is an important equation for us, so I'm going to put this at the top in a yellow box. Now let me just remark, if we did the determinant of minus b, of course that's just minus 1 to the power n for an n by n matrix multiplied by the determinant of b. And of course, because minus 0 is equal to 0, our equation, our characteristic equation, determinant of lambda I minus a is equal to 0, is equivalent to the equation determinant of a minus lambda I is equal to 0. Some books use one equation, some books use the other one. It doesn't matter because they're both effectively the same. You can use whichever one makes more sense to you, whichever one looks easier to you. In this course, I'm mostly going to be using the first one because that's the one that your textbook uses. For example, find all of the eigenvalues of the matrix 3, 0, 8, minus 1. We have our formula at the top. We want to put this a into this formula and then calculate the determinant of lambda I minus a equal to 0 and then see what does that tell us about lambda. So we start like this. We start with our formula. We start with 0 is equal to the determinant of lambda I minus a. And then we put in what we have. Lambda I, lambda multiplied by the identity matrix for a 2 by 2 matrix is just lambda 0, 0, lambda. And then we're going to do minus A. We want the determinant of the 2 by 2 matrix, lambda minus 3, 0, minus 8, lambda plus 1. And of course, we know how to do the determinant of a 2 by 2 matrix. I'll leave it for you to check that this is equal to lambda minus 3 multiplied by lambda plus 1. This is the characteristic equation for this matrix. Which lambda will solve this equation? Of course, lambda equal to 3 and lambda equal to minus 1. So these are the eigenvalues of A. The eigenvalues of A are lambda equal to 3 and lambda equal to minus 1. Let me remark, the formula determinant of lambda I minus A equal to 0, that's the characteristic equation, that leads to the characteristic equation lambda to the power n plus c1, lambda to the power n minus 1 plus dot 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 plus cn to the power minus 1, lambda plus cn equal to 0. If we cross out the equal to 0 in the characteristic equation, we have a polynomial. And this polynomial is called the characteristic polynomial of the matrix A. You'll notice I've put the n's in red. If we have an n by n matrix, then our characteristic polynomial will be an nth degree polynomial, and our characteristic equation will be nth degree polynomial is equal to 0. For example, the one we've just done, the characteristic polynomial of the matrix 3, 0, 8, minus 1 is lambda squared minus 2 lambda minus 3. And that's a polynomial of degree 2. Of course it is, because we started with a 2 by 2 matrix. Find the eigenvalues of this 3 by 3 matrix. First, let's write down the characteristic polynomial. The characteristic polynomial, look in the yellow box, we don't want the equal to 0 if we're doing characteristic polynomial. We want to calculate the determinant of lambda I minus A. And I will leave it for you to check that this is lambda cubed minus 8 lambda squared plus 17 lambda minus 4. Please check that for me, and if I've made a mistake here, please let me know via the discussion board. Take this characteristic polynomial and then write equal to 0, and we get the characteristic equation of the matrix. We want to solve this characteristic equation to find the eigenvalues. Now, we don't know if the eigenvalues are going to be integers or rational numbers or irrational numbers, etc. But we might guess, if we're given something like this as an exam question, probably our teacher's not given us something too hard. So probably at least one of the eigenvalues will be an integer. If you're doing this in the real world, you can't necessarily assume that, but in an exam, you can probably assume that at least one of the eigenvalues will be an integer. So first, let's look to see if there are some integer solutions to this equation. If lambda solves this equation, and if lambda is an integer, then lambda must divide this minus 4 term. Which numbers divide the minus 4 term? 1, minus 1, 2, minus 2, 4, and minus 4. That's the only integers which divide minus 4. So what we're going to do is we're going to try these 6 numbers until we find one which works. I'll start with lambda equal to 1. 1 cubed minus 8 times 1 squared plus 17 times 1 minus 4, and this is equal to 6. This is not 0, so this one didn't work. So let's move to the next one. Let's try minus 1. If we put lambda equal to minus 1 into the characteristic polynomial, what do we get? And you can check that we get minus 30. We do not get 0, so this one didn't work. Let's try again. Next, let's try lambda equal to 2. That didn't work. Lambda equal to minus 2? No, that didn't work. Only 2 left. Lambda equal to 4? Yes. If we put lambda equal to 4 into the characteristic polynomial, then we do get equal to 0. So that means lambda equal to 4 is an eigenvalue. Now we need to look for more eigenvalues. And now that we've found one, it's going to be easier to find some more. Now that we know that lambda equal to 4 is an eigenvalue, it's a root of the characteristic equation, we can factorize our characteristic polynomial into lambda minus 4 multiplied by a quadratic equation. Lambda squared plus some number b, lambda plus some number c. Because we have one y cubed, we know that we must have one lambda cubed, we must have one lambda, and we must have one lambda squared. But we don't know the number b yet, and we don't know the number c yet. If we multiply this out, you can check, we get lambda cubed plus b minus 4 lambda squared plus c minus 4b lambda minus 4c. B minus 4 must be the same as minus 8. C minus 4b must be the same as plus 17. And minus 4c must be the same as minus 4. So we need to have b is minus 4, we need to have c is 1. So our characteristic equation is 0 is equal to lambda minus 4 multiplied by lambda squared minus 4 lambda plus 1. We need to find the roots of this quadratic equation. We need to find the roots of lambda squared minus 4 lambda plus 1 is equal to 0. And we know how to do that. We have a formula that we learned in high school. We have the formula lambda is minus b plus or minus the square root of b squared minus 4ac over 2a. Here, a is 1, b is minus 4, and c is 1. Put these numbers in. You can check that the formula gives us 2 plus or minus the square root of 3. So then we're finished. The eigenvalues of our matrix A are lambda equal to 4, lambda equal to 2 plus root 3, and lambda equal to 2 minus root 3. Next example, find the eigenvalues of this upper triangular 4 by 4 matrix. Now we've looked at determinants of 4 by 4 matrices. Remember that the determinant of a triangular matrix is just a product of the entries on the main diagonal. So the determinant of lambda I minus a, which I've written here, it's lambda minus a11 multiplied by lambda minus a22 multiplied by lambda minus a33 multiplied by lambda minus a44. And then straight away from this characteristic equation, we can see that the eigenvalues of A must be A11, A22, A33, and A4. That's just the entries on the main diagonal of the matrix that we started with. And this method could be used for any triangular matrix, upper triangular or lower triangular or even diagonal. Let's write this as a theorem. If A is an n by n triangular matrix, so it's either upper triangular or lower triangular or diagonal, because diagonal matrices are also triangular matrices, then the eigenvalues of A are just the entries on the main diagonal of A. For example, this is a lower triangular matrix. The eigenvalues of this lower triangular matrix, we don't need to do any work, we don't need the characteristic equation, we don't need any formula, we just look at the entries on the main diagonal, and we can see that the eigenvalues are 1/2, 2/3, and -1/4. Theorem. If A is an n by n matrix, then the following statements are equivalent. I'm just gathering some of the ideas together that we've had before. Lambda is an eigenvalue of A. That's true if and only if lambda is a solution of the characteristic equation. Determinant of lambda I minus A is equal to 0. That's equivalent to saying that the system of equations lambda I minus A x equal to 0 has non-trivial solutions. And what are the solutions? The non-zero solutions are the eigenvectors. And that's equivalent to statement 4. There is a non-zero vector x such that Ax is equal to lambda x. X is the eigenvector. I don't need to prove this because this is just the ideas that we've talked about already. If we want to find the eigenvectors, then we're going to be using the formula lambda I minus A x is equal to 0. First, we'll find the eigenvalues, and then after we find the eigenvalues, we will use this formula to find the eigenvectors. So we have two formulae, which I've now put in the yellow box at the top. The left formula is for eigenvalues, and the right value is for eigenvectors. And there's two different zeros here. In the first equation, that's the equation for eigenvalues, we have equal to the number 0. In the second equation in the yellow box, that's the equation for eigenvectors, we have the 0 vector. Okay, let's do an example. This question tells us that the matrix 1, 6, 5, 2 has eigenvalues -4 and 7, and then we're asked to find the corresponding eigenvectors. So we're going to need to do this twice. First, we're going to do for -4, and then we're going to do it the same idea, but for lambda equal to 7. So first, let's look at lambda equal to -4. We want to take the second equation and we want to put -4 in here. So lambda I minus A x, we want that to be the 0 vector. I've taken the formula, I've changed it around. Lambda I for us is -4, 0, 0, -4, and then minus A. That simplifies to -5, -6, -5, -6, xy. The top line says minus 5x minus 6y is equal to 0. And the second line says exactly the same thing. Minus 5x minus 6y is equal to 0. We can take any x and any y, apart from the 0 vector, we can't have both x and y 0, any non-zero x and y, which satisfy this equation. So, for example, if we wanted to, we could choose x is 6 and y is minus 5. Check that that satisfies the equation. This is an eigenvector of A corresponding to the eigenvalue minus 4. Let's find the second eigenvector. We've done it for minus 4. Now we're going to do the same calculation, but for lambda equal to 7. So this time we're going to take 7 and we're going to put it into the formula. I start with the 0 vector is equal to lambda I minus ax. And I'll leave it for you to check that lambda I minus a is 6 minus 6 minus 5, 5. So we want 0, 0 to be equal to 6x minus 6y, 5x minus 5y. If we take the first line and we divide it by 6, we're going to get a factor radius x equal to y. If we take the second line, and again we divide it, this time divided by 5, again we're going to get x equal to y. When you do eigenvectors of a 2 by 2 matrix, each line, first line or second line, would give you the same equation. Line 2 is just going to be a constant multiplied by line 1. We need a non-zero vector which satisfies x equal to y. You can choose any one you want to. If you want to, you can choose the vector 7, 7. That would be a correct answer to this question. Or you could choose the vector minus 1,234 minus 1,234. That would also be a correct answer to this question. But I like easy numbers, so I'm going to choose the vector 1, 1. This is an eigenvector of A corresponding to the eigenvalue lambda equal to 7. Next, let's talk about Eigen Spaces. Let A be a square matrix, always a square matrix if we're talking about eigenvalues, eigenvectors, and eigenspaces, and let lambda be an eigenvalue of A. The eigenspace of A corresponding to lambda, well, what we want to do is we want to take the set of all eigenvectors corresponding to lambda, but that's not a subspace. Why is it not a subspace? It's not a subspace because it doesn't include 0. Remember, and 0 cannot be an eigenvector. If we take this set and we add in 0, then we do get a subspace. And this subspace is called the eigenspace of A corresponding to lambda. Another way to think about this is the null space of lambda I minus A. So that's all the solutions of lambda I minus ax equal to 0. So all of the eigenvectors and 0 satisfy this equation. We say that again. The eigenspace is the subspace of all eigenvectors and the 0 vector. For example, find bases for the eigenspaces of the matrix -1, 3, 2, 0. The first thing we need to do if we're given a question like this is we need to find the eigenvalues. For the eigenvalues, we use the first equation. Determinant of lambda I minus a is equal to 0. So here we go. We start with that. We start with 0 is equal to determinant of lambda I minus a. We want the determinant of lambda plus 1 minus 3 minus 2 lambda. And when we calculate this determinant, that's the same as lambda plus 1 minus 6, or lambda minus 2, lambda plus 3. And then straight away we can see that the eigenvalues must be 2 and minus 3. This means that there are two eigenspaces of A, one for each eigenvalue. First, we're going to look at the eigenspace for 2, and then we're going to look at the eigenspace for minus 3. An eigenspace is all of the vectors which solve lambda I minus ax equal to 0. We want all of the vectors which satisfy this equation for each one of the eigenvalues. First, let's put in lambda equal to 2. Then we get 3 minus 3 minus 2 multiplied by xy, which is the same as 3x minus 3y, and then minus 2x plus 2y. And we need that to be 0. It doesn't matter which line we choose. Do we choose the first line or do we choose the second line? It doesn't matter because one line will always be the other line multiplied by a constant. Whichever one we choose, we can simplify the equation to x equal to y. That means every eigenvector corresponding to lambda equal to 2 can be written in the form some number t multiplied by 1, 1 for some non-zero number t. What is a basis for this eigenspace then? We'll just take this vector. We'll just take the vector 1, 1. That will give us a basis for the eigenspace corresponding to lambda equal to 2. And then we need to do the same calculation, but for the second eigenvalue, lambda equal to minus 3. So here it is. Here's the whole calculation. If we put lambda equal to minus 3 in, then lambda I minus a becomes minus 2 minus 3 minus 2 minus 3. We need to have that 0 is equal to minus 2x minus 3y, or equivalently, we need to have 2x is equal to minus 3y. What are all the vectors which satisfy this? All of the vectors which satisfy this are of the form s minus 3, 2 for some non-zero number s. And that then tells us that the vector minus 3, 2 is a basis for the eigenspace corresponding to lambda equal to minus 3. Let's do a slightly harder example. Find bases for the eigenspaces of this 3 by 3 matrix. Well, first we need to find the characteristic equation, and then we need to solve the characteristic equation to find the eigenvalues. And I'm going to ask you to check that this is the correct characteristic equation. And then if that's true, we can read off that the eigenvalues of A are lambda equal to 1 and lambda equal to 2. There are 2 eigenvalues, so that means that there are 2 eigenspaces. A non-zero vector x is an eigenvector of A if and only if lambda I minus AX is the zero vector. That's the definition, or that's the formula from the theorem. We need to take this and we need to put lambda equal to 2 in, and we need to put lambda equal to 1 in. First, let's do lambda equal to 2. If we replace every lambda by 2, then we get the linear system 2, 0, 2, minus 1, 0, minus 1, minus 1, 0, minus 1, x, y, z is equal to 0, 0, 0. We need to find all of the solutions to this homogeneous linear system. And how do we solve linear systems? We row reduce the augmented matrix. The augmented matrix is 2, 0, 2, 0, minus 1, 0, minus 1, 0, minus 1, 0, minus 1, 0. And that is row equivalent. That means we can do elementary row operations to change it into 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then we can see that the solution to this is x is equal to minus z, y is a free variable, and z is a free variable. If you're doing row reduction on the augmented matrix for a homogeneous linear system, then the right-hand column is always 0. It doesn't matter which row operations you do, zeros will always stay as zeros. So if you wanted to, you don't have to even write this down. You could forget this, you could ignore this if you wanted to and just do row reduction of a 3 by 3 matrix. Okay, so x must be equal to minus z, y can be any number, and z can be any number. So for z, first of all, let's put in 0, 1, and for the y, let's put in 1, 0. And then we'll use the equation to find x. If z is equal to 1, then x must be minus 1. If z is 0, then x must be 0. Every solution to that homogeneous linear equation can be written in this form. And then as soon as we get to this, we have our two vectors. These are linearly independent vectors. So these are the vectors which form a basis for the eigenspace corresponding to lambda equal to 2. This basis has two vectors in it, so that tells us that this eigenspace is two-dimensional. And then we need to do the same calculation for lambda equal to 1. If we put lambda equal to 1 in, then the linear system that we need to solve is 1, 0, 2, minus 1, minus 1, minus 1, minus 1, 0, minus 2, x, y, z is equal to 0, 0, 0. And I will leave that for you to check. Write down the augmented matrix and then row reduce it, and you will see that the solution is some number t multiplied by minus 2, 1, 1. Straight away, we know then that minus 2, 1, 1 is a basis for the Eigen Space corresponding to lambda equal to 1. This eigenspace is one-dimensional because the basis contains one vector. Next, let's talk about eigenvalues and invertibility. I have a theorem which says that a square matrix A is invertible if and only if lambda equal to 0 is not an eigenvalue of A. And I want to prove this. Let A be any n by n matrix, or any square matrix, and then the characteristic equation will then be an nth degree polynomial is equal to 0. How can lambda equal to 0 be a solution of this equation? It can only be a solution, it's a solution if and only if the final term Cn is equal to 0. So we want to prove that A is invertible if and only if Cn is not equal to 0. If we can do that, then we've proved the theorem. But note that if we take the characteristic polynomial and if we put in lambda equal to 0, then on the left side we just get determinant of minus a, and on the right side we get Cn. And the determinant of minus a is just minus 1 to the power n multiplied by determinant of a. So then straight away we can see the determinant of a is not equal to 0 if and only if Cn is not equal to 0. So A is invertible if and only if Cn is not equal to 0. A is invertible if and only if 0 is not an eigenvalue of the matrix. That's an important idea. For example, this matrix, this 3 by 3 matrix, we've looked at before, we've found that the eigenvalues are 1 and 2. 1 is not 0 and 2 is not 0. 0 is not an eigenvalue of this matrix, so straight away from this theorem we now know that A must be invertible. I'm going to leave it to you to check that this is true by calculating the determinant. If you calculate the determinant of this matrix, you will get a number which is not 0, and then you will be convinced that A is invertible. Here's another important idea. Let A be a square matrix, then the null space of A is the set containing only the 0 vector if and only if lambda equal to 0 is not an eigenvalue of A. Let me prove that. Previous theorem said lambda is equal to 0 is not an eigenvalue of A if and only if A is invertible. But if you look back to lecture 3, look at the invertible matrix theorem, you will see that A is invertible if and only if AX equal to 0 has only the trivial solution. So in other words, A is invertible if and only if the only vector in the null space of A is the 0 vector. And that's the proof. That's useful if you're given an exam question like this. If you're asked to find the null space of a matrix, and if you already know the eigenvalues, and if you already know that the eigenvalues are not 0, then straight away you know that the null space is the set containing only the 0 vector. So if you were given an exam question like this, and if you already have found the eigenvalues, then you can write down that the null space of A is equal to 0. Why? By a theorem from the course. Let's extend these ideas to vector spaces. Let's suppose that T is a linear operator on a vector space V. Then a non-zero vector X in V is called an eigenvector of T, if Tx is a scalar multiple of x. So in other words, if we have the same thing as we had for matrices, if Tx is equal to some scalar lambda multiplied by x. The scalar lambda is called an eigenvalue of t, and x is called an eigenvector corresponding to lambda. So exactly the same idea that we've been talking about, but for linear operators instead of for matrices. Let's talk about similarity again. Let me remind you that two matrices A and B are similar if and only if there exists an invertible matrix P such that B is equal to P inverse AP. These are all square matrices of the same size. Theorem: if A and B are similar, then they have the same characteristic polynomial. But wait a minute, if they have the same characteristic polynomial, then they have the same characteristic equation. And if two matrices have the same characteristic equation, then they must also have the same eigenvalues. Let's prove this. So we're starting by supposing that A and B are similar matrices. So we're starting by supposing that B is equal to P inverse AP. Anytime we're doing a proof of similar matrices, we're going to start with B is equal to P inverse AP. And then I'm going to calculate P inverse A minus lambda I P. I get P inverse AP, okay. Lambda is a number, we can put that anywhere we want, so let's put that first. And then P inverse IP, or P inverse P, is just the identity. We just get B minus lambda I. Okay, so if these two things are the same, then they must have the same determinant. The determinant of B minus lambda I must be the same as the determinant of P inverse A minus lambda IP. But because P is an invertible matrix, the determinant of P inverse is just 1 divided by the determinant of P. And then, of course, they just cancel out, and we're just left with the determinant of A minus lambda I. That proves that if A and B are similar matrices, then they have the same characteristic polynomial. And of course, if they have the same characteristic polynomial, then they must have the same eigenvalues. Now, this implication goes one way. If A and B are similar, this implies that A and B have the same eigenvalues, but the converse is not true. It's not true that if A and B have the same eigenvalues, then A and B are similar. As a counterexample, I offer you these two matrices, 2, 1, 0, 2, and 2, 0, 0, 2. These are both triangular matrices, so straight away we can look at the main diagonal and see that the eigenvalues is just 2. So both of these matrices have the same eigenvalue, but these matrices are not similar. It's not possible to find an invertible matrix P such that P inverse AP is equal to B. I also want to remark that similarity is not the same as row equivalence. Elementary row operations can change a matrix's eigenvalues. Okay, let's move on to our second topic, the idea of diagonalization. a square matrix A is said to be diagonalizable if and only if it's similar to some diagonal matrix. If somebody asked you to tell them the definition of a diagonalizable matrix, then you would write that a square matrix A is diagonalizable if and only if it's similar to some diagonal matrix. What does that mean? That means it's diagonalizable if and only if there exists an invertible matrix P such that P inverse AP is diagonal. In this case, we say that the matrix P diagonalizes A. So how do we know if a matrix is diagonalizable? We have this nice theorem. This is an important theorem for this topic. If A is a square matrix, a square n by n matrix, then A is diagonalizable if and only if A has n linearly independent eigenvectors. And there's sometimes a shortcut to find if A has n linearly independent eigenvectors. If A has n distinct or different eigenvalues, then A has n linearly independent eigenvectors, which then implies A is diagonalizable. I'm not going to prove this theorem, but this is a very important one. Make sure that you learn this one. So, how do we diagonalize a matrix? This is going to be our method. A is going to be an n by n square matrix. Step 1, we need to check to see if A is diagonalizable. And we do that by searching for n linearly independent eigenvectors. If we can find n linearly independent eigenvectors, then A is diagonalizable, and we can continue. If there do not exist n linearly independent eigenvectors, then A is not diagonalizable. Let's suppose that we can find n linearly independent eigenvectors. Then I'm going to call these eigenvectors P1, P2 up to Pn. Step 2, I'm going to write down the n by n matrix capital P, which has first column P1, second column P2, etc. And then step 3, I want to calculate P inverse AP. So let me repeat that. First, we need to find n linearly independent eigenvectors. And then we're going to write down the square matrix, which has first column, first eigenvector, second column, second eigenvector, and so on. Then we want to do P inverse AP. But before we do an example, let's take a 10-minute break. And let's continue. We want to diagonalize a matrix. The way we're going to do this is step one, we need to find n linearly independent eigenvectors, and we're going to call these P1, P2 up to Pn. Step two, we're going to write down the square n by n matrix capital P, which has first column first eigenvector, second column second eigenvector, and so on. And then step three, we're going to calculate P inverse AP. For example, find a matrix capital P which diagonalizes this 3 by 3 matrix 0, 0, minus 2, 1, 2, 1, 1, 0, 3. We've looked at this one already today. We've already found that the eigenvalues are 2 and 1. And we've also found bases for each eigenspace. P1 and P2, written here, form a basis for the eigenspace corresponding to lambda equal to 2, and P3 forms a basis for the eigenspace corresponding to lambda equal to 1. So we've done most of the work already. We have our 3 linearly independent eigenvectors. Step 2 is to write down the matrix capital P. We want the square 3 by 3 matrix where the first column is the first eigenvector, it's minus 1, 0, 1. The second column is the second eigenvector, 0, 1, 0. And the third column is the third eigenvector, minus 2, 1, 1. This is the matrix which diagonalizes A. To check that we haven't made a mistake, we can calculate P inverse AP. And I leave it for you to check that if we multiply these 3 matrices together, we get the diagonal matrix 2, 0, 0, 0, 2, 0, 0, 0, 1. Now, let me just remark that this diagonal matrix, which I'm going to call D, what are the entries on the main diagonal? The entries on the main diagonal are the eigenvalues of A. The eigenvalues were 2 and 1. The eigenvalue 2 corresponded to a 2-dimensional eigenspace, so we have 2 lots of 2. The eigenspace corresponding to 1 was 1-dimensional, so that's why we only have one number 1 on the diagonal. I also want to remark that when we wrote down P, we used 2 eigenvectors corresponding to lambda equal to 2 in the first 2 columns. That's why we have 2 in the first position and 2 in the second position. When we wrote down P, we used an eigenvector corresponding to 1 in the third column. So that's why we get a 1 in the third position. That's why it goes 2, 2, 1 when we go down this main diagonal. I'd also like to remark this is not the only matrix which diagonalizes A. We didn't have to write the eigenvectors in this order. If we wanted to, we could write the eigenvectors in a different order. Let's suppose we switch the second column and the third column around. Then we would get a new matrix Q, which also diagonalizes A. The columns of Q are still linearly independent eigenvectors of A, so Q still diagonalizes A. But if we calculated Q inverse AQ, again, we'd get a diagonal matrix. But because we're using first an eigenvector corresponding to 2, and then an eigenvector corresponding to 1, and then an eigenvector corresponding to 2, if we look down the main diagonal, the numbers are 2, 1, 2. Another example, show that this 3 by 3 matrix is not diagonalizable. First, we need the eigenvalues and the eigenvectors. So what we do, we take our characteristic equation, 0 is equal to the determinant of lambda I minus A, calculate this and factorize it to lambda minus 1, lambda minus 2 squared, and then we can see that the eigenvalues are 1 and 2. Actually, no, we don't want to do this. This is a triangular matrix. If we have a triangular matrix, we can read off the eigenvalues straight away. We don't need to waste our time doing characteristic equation for a triangular matrix. Straight away, we can see that the eigenvalues are 1 and 2. And then we want to find bases for the eigenspaces of A. And this one I'm not going to do the calculation for. I'll leave this for you to check. Please check that these two vectors, this should be P2, are bases for the eigenspaces of A. The eigenspace corresponding to 1 is one-dimensional, and the eigenspace corresponding to 2 is also one-dimensional. That means that we have a 3×3 matrix, but we only have 2 linearly independent eigenvectors. We do not have enough linearly independent eigenvectors to write down P, so A is not diagonalizable. By the theorem from the break, a matrix is diagonalizable if and only if we have n linearly independent eigenvectors. What about this one? Is this matrix diagonalizable? This is another one which we've looked at already today. We've already found that the eigenvalues of this matrix are 4, 2 plus root 3, and 2 minus root 3. We have 3 different eigenvalues, or 3 distinct eigenvalues. The theorem said if we have 3 distinct eigenvalues, then we must have 3 linearly independent eigenvectors. So IA must be diagonalizable. If we have 3 distinct eigenvalues, then we don't need to do any more work. That's enough to tell us that the matrix is diagonalizable. Another example, this one from a textbook. Because the eigenvalues of a triangular matrix are the entries on the main diagonal, this matrix has eigenvalues -1, 3, 5, -2. We can say that a triangular matrix is diagonalizable if and only if the entries on the main diagonal are all different numbers. This matrix has 4 different numbers on its main diagonal, 4 different eigenvalues, so this matrix must be diagonalizable. Let's talk about the eigenvalues of powers of a matrix. Suppose that we know the eigenvalues and eigenvectors of a matrix A. What are the eigenvalues and eigenvectors of A to the power k? Well, we're supposing that we know lambda and x, which satisfy this equation. But then a squared x, which is a multiplied by ax, or a multiplied by lambda x. Lambda is a number. We can just take lambda outside to get lambda multiplied by ax, or lambda x, or lambda squared x. That tells us that lambda squared is an eigenvalue of a squared with corresponding eigenvector x. So when we go from a to a squared, we square the eigenvalues, but the eigenvectors stay the same. And of course, that's true for any power. Let's write that as a theorem. Let k be any natural number. If lambda is an eigenvalue of a, and x is a corresponding eigenvector, then if we want to find the eigenvalues of AK, we do lambda to the power k, but x stays the same. Lambda to the power k is an eigenvalue of AK with corresponding eigenvector x. For example, this 3 by 3 matrix, it's a triangular matrix, so straight away we can see the eigenvalues. This has eigenvalues 1 and 2. And I will tell you the corresponding eigenvectors are 1, -1, 8, and 0, 0, 1. Find the eigenvalues and eigenvectors of a to the power 7. Well, we have our theorem. All we want to do is take the eigenvalues, that's 1 and 2, and put them to the power 7. So 1 to the power 7 is 1, 2 to the power 7 is 128. These are the eigenvalues of a to the power 7. And what are the eigenvectors? The eigenvectors stay the same. P1 and P2 are also eigenvectors of a to the power 7. Let's talk about computing powers of a matrix. Diagonalizing a matrix A makes calculating a to the power k much easier. Why? Well, first of all, let's suppose that A is a diagonalizable matrix. That means we can find a matrix P such that P inverse AP is equal to a diagonal matrix D. And then if we square both sides, remember how easy it is to square a diagonal matrix. P inverse AP squared is D squared, and D squared is just the diagonal matrix where we have lambda 1 squared, lambda 2 squared, etc. down the main diagonal. However, D squared, that means P inverse AP all squared. We're doing P inverse AP multiplied by another P inverse AP. But P inverse in the middle is going to cancel out, and we'll just end up with P inverse A squared P. So in other words, P inverse A to the power kp for any k, of course, is just D to the power k. That's this diagonal matrix with the eigenvalues to the power k down the main diagonal. And then we can rearrange this to the formula A to the power k is P, D to the power k, P to the power -1, P inverse. Why is that useful? Because D to the power k is very easy to calculate. We just take the numbers on the main diagonal and put them to the power k. So really, to calculate a to the power k, we don't have to do a times a times a times a times a, which might take us a long time. Really, we just need to multiply 3 matrices together. For example, find a to the power 13 if A is this matrix. We've looked at this one earlier. We've seen that A is diagonalizable. We see it's diagonalized by this matrix P, and we've seen that P inverse AP is the diagonal matrix 2, 0, 0, 0, 2, 0, 0, 0, 1. So, using the formula in the yellow box, A to the power 13 is P, D to the power 13, P inverse. And D to the power 13, that's very, very easy. That's just the diagonal matrix with the entries 2 to the power 13, 2 to the power 13, and 1 to the power 13, or just 1 on the main diagonal. So to calculate a to the power of 13, we don't have to do a times 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 a. We just need to multiply these three matrices together. That saves a lot of work. And I'll leave it for you to check that if we multiply these three matrices together, we get this one, which, yes, is a little bit complicated, but it's not as difficult, it's not as complicated as doing a times a times a, etc. Let me remark that if A has n distinct eigenvalues, then we know that A is diagonalizable. But the converse is not true. It's not true that every diagonalizable matrix has n distinct eigenvalues. For example, consider the matrices I and J written here. I'll leave it for you. Well, both of these are triangular matrices, so we can see the eigenvalues straight away are lambda equal to 1. However, I has 3 linearly independent eigenvectors, but J has only 1 linearly independent eigenvector. Please check that. This means that I is diagonalizable, but J is not diagonalizable. And that's enough about diagonalization for now. We will come back to this idea of diagonalization in future weeks. We'll talk about a more advanced type of diagonalization called orthogonal diagonalization. And then in the final week, we will talk about a more sophisticated form of factorization called singular value decomposition. For now, I want to change topic and talk about complex vector spaces. Why is that interesting to us? Well, I start with the example, find the eigenvalues of -2, -1, 5, 2. We need the characteristic equation. 0 is equal to the determinant of lambda I minus a. And I'll leave it for you to check. That is equal to lambda squared plus 1. What are all the solutions to lambda squared plus 1 is equal to 0? The solutions are I and minus I. This is a real 2 by 2 matrix, but the eigenvalues are complex numbers. So it's time to start talking about complex numbers again. Let's talk about vectors in c to the power n. What does that mean? That means a sequence, a finite sequence of n complex numbers. A vector in c to the power n is a complex n-tuple. That's a sequence of n complex numbers. And then the set of all of the vectors like this is called complex n space, and we write it as c to the power n. When we talk about complex vector spaces, the scalars are going to be complex numbers, and anytime we do addition, subtraction, or scalar multiplication, we're just going to be doing these component-wise. For example, U is the vector 1 plus I, and then minus 4i, and then 2 plus 3i. We've got 3 complex numbers in a vector, so this is a vector in C3. Likewise, 0i5 is a vector in C3, and 6 minus root 2i, 9 plus a half I, pi I is also a vector in C3. Every complex vector can be split into real and imaginary parts. We take the real part, that's the A1, A2, etc., up to AN. Write that first, that's the real part of the vector. And then we take the B terms, B1, B2, etc. Write those as a vector and then multiply by I. That's the imaginary part of V multiplied by I. the complex conjugate of a vector v, all we do is that we take the complex conjugate of each component. We change a1 plus b1i to a1 minus b1i, and so on. Every time we have a plus in front of the I, we change it to a minus. Every time we have a minus in front of the I, we change it to a plus. We could write this as the complex conjugate of v is equal to the real part of v minus the imaginary part of v multiplied by I. We can think of r to the power n as a subset of c to the power n. We have the rule that r is a real vector, r is in Rn, if and only if the complex conjugate of v is equal to v. Now, I've written something else here. I've written that Rn is not a subspace of Cn. Why is that true? That's not true because when we talk about complex vector spaces, our scalars are complex numbers. If we take a real vector, let's say we take the real vector 1, 1, and if we multiply it by I, then we get a vector which is not in R squared. R squared is not a subspace of C squared because it's not closed onto scalar multiplication. For example, if v is the vector 3 plus I minus 2i, 5, then the complex conjugate, change every plus in front of I to minus, every minus in front of I to a plus, is 3 minus I plus 2i, 5. The real part of v is 3, 0, 5. 3, and then there's a 0 minus 2i, and then 5. And the imaginary part is the numbers in front of the I, well, 1, minus 2, and then plus 0i. 1 minus 2, 0. We can also talk about complex matrices. The set of all m by n complex matrices is going to be c to the power m by n. If A is a complex matrix, it's a matrix where the entries can be either real numbers or complex numbers. This if shouldn't be here. The real part of A and the imaginary part of A, just as you would expect, that we just take the real part and the imaginary part of each one of the entries of A. Likewise, we can talk about the complex conjugate of a matrix just by doing the complex conjugate of each entry in A. So, for example, if A is the 2 by 2 complex matrix, 1 plus I minus I, 4, 6 minus 2i, we can do complex conjugate by doing the complex conjugate of each entry. 1 plus I changes to 1 minus I changes to plus I, 4 stays the same because 4 is just a real number, 6 minus 2i changes to 6 plus 2i. The real part of A is 1, 0, 4, 6, and the imaginary part of A is 1 minus 1, 0, minus 2. We can do the determinant of A in the usual way. 1 plus I multiplied by 6 minus 2i, and then minus I multiplied by 4. And if you multiply this all out, you can check that this is equal to 8 plus 8i. Two theorems which are pretty much the same. The first one is for vectors and the second one is for matrices. The complex conjugate of the complex conjugate of v is just v. If I have a number k complex number k, no, a complex vector v multiplied together. Complex conjugate of kv is the complex conjugate of k multiplied by the complex conjugate of v. And if I have two vectors, I want to add them together. The complex conjugate of a plus v is the same as the complex conjugate of u plus the complex conjugate of v. I'm not going to prove that. You can do that. The idea is to come straight away from the rules for complex numbers. And then we have the same idea for matrices. I'm just being careful about the sizes of the matrix first of all, because I want to multiply them together. Let's not worry about that for now. Complex conjugate of the complex conjugate of A is A. If we do a transpose, doesn't matter if we do complex conjugate first and then take the transpose, or we do the transpose first and then take the complex conjugate. Two matrices A and B multiplied together. We could multiply them together first and then do the complex conjugate, or we could take their complex conjugates first and then multiply them together. It doesn't matter. And the same for if we have a number multiplied by a matrix. Now, actually, Theorem 2 implies Theorem 1 because a vector is just an n by 1 matrix. So if we could prove that this is true for all matrices, then straight away, free of charge, we would have the first theorem. So don't bother proving the first theorem. If you want to, prove the second theorem, and then you have the first one free of charge. Let's talk about eigenvalues and eigenvectors of a real matrix. We've seen that sometimes real matrices can have complex eigenvalues. Let's talk about this situation. And I'm starting with this theorem. Suppose that A is a real n by n matrix. In other words, A is in R n by n, or if you want, is equal to m subscript nn. Suppose that lambda is an eigenvalue of A, and let's suppose that x is an eigenvector of A corresponding to lambda. The theorem says then the complex conjugate of lambda is also an eigenvalue of A with corresponding eigenvector complex conjugate of x. And I want to prove this. We're starting by supposing that ax is equal to lambda x. We're starting by supposing that lambda is an eigenvalue and that x is a corresponding eigenvector. And because we have a real matrix, we have a matrix where the complex conjugate of A is equal to A, because that's what we always have for real numbers. And then the calculation goes like this. I want to show that the complex conjugate of x is also an eigenvector of A. So I'm going to start with A multiplied by complex conjugate of x. And as we've seen, the complex conjugate of the product of two matrices, because a vector is a type of matrix, vector is an n by 1 matrix, we just take the complex conjugate of each term. But complex conjugate of A is just A. So that's complex conjugate of AX, but AX is lambda x. Yeah. And that's just complex conjugate of lambda, complex conjugate of x. And that's the whole proof. A multiplied by the complex conjugate of x is equal to lambda, complex conjugate of lambda multiplied by the complex conjugate of x. Okay, great. So if we can find one eigenvalue of A, and if it's a complex number, then we have another one straight away. Free of charge, no more calculations, we know the second one. Likewise, if we know an eigenvector of A, then straight away we could just do its complex conjugate and we get another eigenvector. So it's like find one eigenvector and get one free. Find the eigenvalues and bases for the eigenspaces of this 2 by 2 matrix. First, eigenvalues. So we need the characteristic equation. The characteristic equation is 0 is equal to lambda squared plus 1. So as we did earlier, the eigenvalues are I and minus I. Note that these are complex conjugates of each other. And then step 2, we need to find the eigenvectors. For eigenvectors, we have the formula 0 vector is equal to lambda I minus a x. And for this matrix, that's lambda plus 2, 1, minus 5, lambda minus 2 multiplied by xy. First, we do lambda equal to I, and we get this linear system. We want I plus 2, 1, minus 5, I minus 2, xy is equal to 0, 0. The first line says I plus 2 multiplied by x plus 1 multiplied by y is equal to 0. We can choose any non-zero x and y which satisfies this equation. Now, I like easy numbers, so I'm going to choose one of these to be equal to 1. I could choose x is 1, or I could choose y is 1. For this example, I'm going to choose x is equal to 1, and then I'm going to rearrange the equation, and I find that y must be then minus 2 minus I. And then we also need an eigenvector corresponding to minus I. But before I say that, I've said that when we do 2 by 2 eigenvectors, once we get to this point, the second line should always be the same as the first line, but multiplied by a number. In other words, the second line in this above equation must be the same as the first. But why? Well, because if we take the first line says I plus 2x plus y is equal to 0. And if we multiply this by I minus 2, why? Because I want to go from 1 to I minus 2. So I'm going to multiply by I minus 2. Multiply both sides by I minus 2. I get I minus 2 multiplied by I plus 2, x, plus I minus 2, y is equal to 0. But what is this? I minus 2 multiplied by I plus 2 is just minus 5. The second line of this equation is just I minus 2 multiplied by the first line. So always, when you do this, as long as you don't make a mistake in your calculations, the second line should just be the same as the first line multiplied by a number. So pick whichever line looks easiest to you. Next, we need an eigenvector corresponding to minus I. We could use the same method. We could use the equation for an eigenvector. But of course, there's an easier way. The theorem said all we need to do is take the complex conjugate of the first eigenvector. The first eigenvector was 1, minus 2, minus I. We're just going to take the complex conjugate of this. 1 is a real number, so that stays the same. Minus 2 stays the same as minus 2, and minus I, we change the sign, it becomes plus I. And that's all we need to do to find the second eigenvector. So it's calculate one eigenvector and then get the other eigenvector free of charge. Another idea, let's talk about eigenvalues of 2 by 2 matrices. Consider a general 2 by 2 matrix, A, B, C, D. The characteristic polynomial of this, that's determinant of lambda I minus A, or lambda squared minus A plus D, lambda plus AD minus BC. But wait a minute, these two numbers, A plus D and AD minus BC, these should look familiar to you. A plus D, what's that? That's just a trace of A. And AD minus BC is the determinant of A. The characteristic polynomial of a 2 by 2 matrix is always lambda squared minus the trace of the matrix lambda plus the determinant of the matrix. Put an equal to 0. The characteristic equation of a 2 by 2 matrix is always lambda squared minus the trace of A lambda plus the determinant of A is equal to 0. And we're going to be talking about this, so I'm going to put this up the top in the yellow box. Now, we know from high school that the roots of a quadratic equation are given by this formula, minus b plus or minus the square root of b squared minus 4ac over 2a. And we know that there are going to be 3 cases to consider. If b squared minus 4ac is a strictly positive number, then there must be 2 real roots. If b squared minus 4ac is equal to 0, then there's going to be 1 repeated root. And if b squared minus 4ac is a negative number, then we're going to have complex conjugate roots. We have a quadratic equation like this. For us, a is 1, b is minus the trace of a, so b squared is the trace of a squared, and c is the determinant of a. So we can say that a 2 by 2 matrix A has 2 distinct real eigenvalues if the trace of A squared minus the 4 times the determinant of A is strictly positive. And that's the same as saying that if the trace of A squared is bigger than 4 times the determinant of A, and A must have 1 repeated eigenvalue if the trace of A squared minus 4 times the determinant of A is 0. Or to say it another way, if the trace of A squared is the same as 4 times the determinant of A. And finally, we know that we're going to have 2 complex conjugate eigenvalues if the trace of A squared minus 4 times the determinant of A is a negative number. In other words, if the trace of A squared is smaller than 4 times the determinant of A. Let's look at some examples. Find the eigenvalues of the 2 by 2 matrix 2, 2, minus 1, 5. Here, the trace is 7, 2 plus 5 is 7, and the determinant is 12. The trace squared is 49, 4 times the determinant is 48. So the trace squared is bigger than 4 times the determinant. So we know this matrix must have 2 distinct real eigenvalues. The characteristic equation, lambda squared minus the trace lambda plus the determinant, so minus 7 lambda plus 12. We can factorize that to lambda minus 4, lambda minus 3. And yes, we have 2 distinct real eigenvalues. Let's do another one. Find the eigenvalues of 0, minus 1, 1, 2. the trace is 2 and the determinant is equal to 1. This is an example where the trace squared is equal to 4 times the determinant. That means we're going to get 1 repeated eigenvalue. We could write down the characteristic equation straight away. 0 is equal to lambda squared minus the trace of lambda plus the determinant. That's lambda minus 1 squared. So lambda equal to 1 is the only eigenvalue of A. And find the eigenvalues of 2, 3, minus 3, 2. What's the trace? The trace is 4. What's the determinant? The determinant is 13. Clearly here, the trace squared is smaller than 4 times the determinant. So we know that we must have complex conjugate eigenvalues. And if we calculate them, we find that yes, we do. We have 2 plus 3i and 2 minus 3i. But I leave that for you to check. I'm coming to the end of the lecture now. I have 2 more ideas. First idea is about eigenvalues of symmetric matrices. If A is a real symmetric matrix, that's a matrix, a square matrix of any size, not just 2 by 2 like the previous ideas, it could be any size, then A has real eigenvalues. I'm not going to prove that. And the final idea for this week's lesson is about an interpretation of complex eigenvalues. If you think back to the start of today's lecture, I said matrices do things to vectors. And I was talking about how an eigenvector is a special vector which gets stretched but doesn't rotate. But what does that mean for complex eigenvalues? This theorem says that the eigenvalues of the real matrix A minus B, BA are A plus or minus BA. And if these are both not 0, we can factor up this matrix like this. We can have absolute value of lambda, or because lambda is a complex number, modulus of lambda, 0, 0, absolute value of lambda, multiplied by cos phi minus sin phi, cos phi, where phi is the argument of A plus lambda, A plus BI. What does that mean? That means, look in this picture, it means this angle here. So geometrically, that means that this matrix does a rotation first of all. This is the matrix of a rotation first, and then it does a scaling, because the other matrix is the matrix of a scale. So what this matrix does is it takes a vector v, and first it rotates it by the angle phi, and then it scales it. But that's enough for this week. Next time, we're going to talk about inner product spaces, orthogonality, and orthogonal sets and orthonormal sets. Are there any questions?